mostly works for larger planets like Jupiter-like objects. So for a gas giant, it's relatively easy for the scientists to determine mass this way. For smaller planets, terrestrial planets, especially planets that only represent a fraction of the total mass of the star system, that method would not really work very well. You would need to have an extremely accurate telescope, which doesn't actually exist yet. Just to give you a comparison of mass difference here, the total mass of all of the TRAPPIST-1 planets represent about 0.02% of the total mass of the star system. Now that's almost nothing. That's actually kind of similar to the amount of mass in all of the moons of Jupiter compared to the mass of Jupiter, which, by the way, does imply that these particular planets may have been created in a very similar way to the moons of Jupiter. There is actually a very unusual similarity in different orbital patterns and also just in the way that the planets behave compared to the moons of Jupiter. And so, by just knowing the sizes of these planets, how did the scientists determine their mass then? Well, there's actually a very interesting method known as TTV, or transit timing variation. This method also relies on measuring the shadows of these planets passing in front of the star. But in this case, when there's another object in the star system, such as, for example, another massive planet nearby, it will start moving on this planet, thus affecting when the shadows appear compared to our original predictions. So in this case, because of the pull from this planet, the transits now, the shadows, will have slightly different timing. There will be a timing variation. Now this transit timing variation is a very, very precise and actually very interesting method of determining the total masses of all of these planets. And so by looking at transit timing variations of all 7 planets, after only a few months, the scientists were able to calculate very precise masses of each of these planets, where the transit timing variation made a lot of sense. And now we know as a fact what the mass and the size of each of these planets is, with the recent study being the most accurate in determining both. And once you know the size and the mass of each of these planets, finding the density is just a matter of division. Dividing one value by the other, you get the total density of each of these planets. Now, what's really unusual is, of course, the recent discovery and the recent confirmation that the density of each of these planets is very unique to anything we've seen so far. Each of these planets seem to have extremely similar density to each other, and that's something we've never seen before, with the overall planetary density being very, very similar to planet Earth and also very similar to each other. It's defined as being about 8% less than the density of Earth and the
What do you call a hot wild pig butt? Thermal borehole. Joke brought by Alpha Centauri.
density of Venus. And remember, here we're talking about 7 unique planets, 7 planets that most likely also have somewhat different surfaces, somewhat different atmospheres, and potentially somewhat different composition as well. But in this case, they do have very similar density, and that just kind of doesn't make sense right now. The reason it does make sense is because of the examples we have from the solar system, and actually really from any star system we've seen so far. So just as a comparison, let's take a look at the solar system and the density of planets here. The highest density of all of the objects is our own planet Earth. The density here is about 5.5 grams per centimeter cube. Then we have the neighbor Venus, then we have Mercury, and then we have Mars, with the density of Mars being about 3.93 grams per centimeter cube. Now, usually by knowing these densities, we can then determine what the composition of the planet is and also what sort of materials we can expect to find both inside the planet and possibly even in the upper regions of the planets. Now, in this case, we know that Mars, for example, doesn't really have a very large iron core, whereas Mercury, despite its smaller size, probably has a much larger core. And then once we start talking about gas giants, the densities suddenly drop. With the least dense object of all being Saturn, the density here is actually less than the density of water. It's about 0.68 grams per centimeter cube. And so here, that's kind of what we expect from most of the planets in the typical star system. And for the most part, we've been seeing something similar in other star systems as well. Even if you were to look at the moons of Jupiter, their densities do vary quite a lot. Not as much as the density between Earth and Saturn, for example, but still quite a lot, between 1.83 grams per centimeter cube for Callisto and 3.53 grams per centimeter cube for Io. But somehow none of this seems to work for TRAPPIST-1 planets. Each of the planets here, despite the distances to the star and despite their location in the star system, seem to have relatively similar densities, even if their size or their mass is different from the planet next to it. And at the moment, nobody really knows how to explain any of this. There are three potential explanations, but none of them are really conclusive. The first explanation here is really in regards to the cores of these planets. All seven of them might have relatively similar iron cores that are slightly smaller than the core of planet Earth, with the iron cores inside each of these seven planets being roughly around 21% of the total mass of each of these planets. But having a core that's pretty much exactly the same as the core of the planet next to it is very unusual, or it would be almost impossible to explain this in any of the modern planetary formation theories today. Why would these planets have exactly the same internal structure? Currently, there's really no way to explain this. And also, just to give you a comparison, Earth has the core that's about 32% of the total mass, and it's that iron core that gives our planet such a high density. And it's also the biggest iron core of all of the terrestrial planets in the solar system. The second explanation that kind of makes sense is maybe because all of these seven planets are filled with iron oxides. You know, that same stuff that makes the surface of Mars red? But unlike surface of Mars, all of this would be going all the way down to the core. Now that's a very good explanation as well, but it still doesn't make sense that all seven of them would have this. We know, for example, that several moons of Saturn and Jupiter, such as Titan right here, do have a kind of a strange mixture on the inside where these silicates are mixed with different water compounds and form these unusual structures on the inside that give them very specific densities. Something similar could happen if you were to mix metals, or iron in this case, with various oxygen compounds. But there should still be some difference. It's still kind of difficult to imagine that all seven planets would have exactly the same densities and exactly the same structures. And the last and the third explanation here is, well, it's also kind of unusual, but kind of makes more sense. In this case, the scientists imply that it's possible that the large amount of mass of each of these planets is made out of water. And more specifically, the middle planets here would most likely contain some sort of a liquid ocean. The outer planets would be made out of really large amounts of ice, but the inner planets, specifically the three inner planets, would have a very large atmosphere of water gas, which would also in turn increase their overall size. Kind of similar to the very thick atmosphere we see around Venus, for example. And for this explanation to work well, each of these seven planets would have to have a very specific amount of water on the surface. It doesn't really matter what they have on the inside, they'll probably still have different cores and different iron composition, but the presence of water has to differ in order for them to have these properties that we're observing and to have the sizes and the masses that we're seeing, which also implies that at least three of these planets potentially have a liquid ocean on the surface. But here on some of these planets, this would also mean that water would have to represent about 5% of the total mass of the planets, especially the outer four planets. Whereas if you were to look at planet Earth, our planet only has about 1% of mass being water. But of all of these three ideas or three propositions, the one about water actually makes the most sense right now. Although it's also possible that it could actually be a combination of two or even three of these propositions. So maybe there is a lot of water on some of these planets, but they also contain a lot of iron oxides as well, and possibly even some sort of an iron core. So all three ideas and three propositions currently kind of make sense. Nevertheless, all these discoveries of TRAPPIST-1 present the star system as one of the most unique star systems we've ever discovered, with seven planets that are extremely interesting for many different reasons. Some of which, of course, being the fact that they probably contain liquid oceans, and also don't seem to be very different from planet Earth in terms of the mass, size, and of course density. Now, whether they actually look like this picture right here, and whether we discover signs of potential life here, is unfortunately not something we're going to know until we take a look at these planets with more powerful telescopes. Luckily, James Webb Telescope should be able to tell us a lot more about this star system in the next few years. But for now, that's all we know about this unusual star system. We seem to be discovering new things about it every single time there's a new study, and we seem to be discovering new mysteries as well. But hopefully, in the next few years, we'll have a definitive answer about what's really happening in the star system and whether we're going to find something absolutely incredible on the surface of these unusual planets. One day we might be able to visit them, but it's probably not going to be anytime soon. But anyway, that's all I wanted to mention for now. Check out the study I mentioned in the description below and all of the additional information there as well. If you've enjoyed this video, subscribe, maybe share this with someone who loves learning about space and sciences.
And as always, have a good day. By the way, the picture I used for this radio is the essentially finals picture I did for my school. I learned all that you could about the basics, like what is programming when you take it away from the language, what kind of logic needs to exist for it to be programming. When it came to the nitty gritty of learn how to animate an object with this thing, I didn't learn much because I already knew animation. And what they wanted us to do was essentially use a single program, get a entry-level programmer job after an interview with one of the companies and work from that. But I made it pretty clear that I have one reason for coming there. I failed my college Swedish and I can only get the GED or college equivalency thing, whatever, if I get my Swedish classes passed somewhere. And I learned that you can, instead of switching to a lower end college, you can do a double degree, meaning that you do some other form of manual labor preparation school where you get accredited for Swedish with basically zero effort, and then I can go back to my school. The problem with my school was that it was the best adult college in the city, but it was in the Swedish neighborhood, but they taught in Finnish and English. So their demands as to how well you had to learn Swedish were something else entirely when you compare it to an occupational school where you take one course and everybody passes. So I took something I knew I was gonna be like passable no matter what I did, and it was programming with a specialty in game testing. The classes were 70-80% stuff that I knew already. 10% of it was too hard for me unless I really buckle down and learn it. And about 15% was interesting and new. And the stuff that was interesting and new was the stuff that I all basically learned. So if I look at somebody's thought map, bubble map, and it has those if and arguments and various colored regions, and all of them have the same colors and shapes, I know what those are supposed to mean. I know the symbology of the language, and I can add and subtract from it to create functions. But doing this with a computer requires me to learn that specific computer's programming language. I have learned a few, but they have always been program specific. Every programmer seems to write things differently. So I could spend my time learning 10 languages that may or may not be used by anybody by the time I get to work. Or I can learn the act of learning a language really well, meaning that I know what is uniform between languages, etc. And I focused on that. So if you put me to a programming work now, it'll take me about 3 months to start producing quality code. I can start producing code in a day, but for it to be something worth selling to a customer, give me 3 months. Put me in game testing of a product that you've already launched or is low interest if it's going to be launched currently. It may be, but it has to be low interest. Give me like a week to play it, and I will make you the longest recommendations of bugs that you've ever seen. Bug reports and recommendations on features to add and things to change. It will be the longest list that you've ever. And one of the good grades I got in college was for essay writing. Philosophy, psychology, history, religious studies, atheist studies, what have you. Religious studies from the point of view of the religion and religious studies from the point of view of the disbeliever. I took both classes. We have those. In this country, you're supposed to say which group you belong to and then take their religious classes. So, I took both. Some of the classes I took, because I took so many and repeated them so many times, were frowned upon slightly, but most teachers were kind and, happy to see me, if that can be called happiness, but, in the mood to teach. We took all classes where my grade average was, I think it's C in your system or B. We took them until I had in the things that interested me a grade average above B. And most of the classes ended with a grade average of A- to A. Took me a while. Did it at my own leisure. Wrote a book, campaigned for politics, campaigned for parliament actually, and also for municipal. Joined a new party, did alternative healthcare research, did 2 weeks of military service, 3 months of conscientious objector service, and about 2 months of prison. Long story. I did a lot of stuff while studying. I aimed for about 20, 30 years in work life and 20, 30 years before that and 20, 30 years in pension. That's what I aimed for. It's my rough outline. Would be in my age interest to live until I'm about 90. And to live the first 25, 30 years completely unto myself, to do only the things which interest me. After that, to find something that others are interested in me doing repeatedly, then proceed to do that repeatedly, and then 30 years with or without someone. It depends on the 60 years before that, but then 30 years after, I am not interesting to others to just roam. Then I can one day lie down and wake up as somebody else. My understanding of the process. Don't know what your belief is, but I believe the universe wastes nothing, and wasting a human mind is a terrible effort. It takes quite a lot of effort to waste your mind, so I know about wasting a mind. That doesn't mean that there isn't final death. It doesn't mean that. It just means that it shouldn't be associated with the death of the body. And to be understood as a continuous process, which happens many times across your life. If you understand that, then you understand what scientists are calling telomeres. Every time you make a conscious split from what you were building, where you keep both of them alive but ignore the other, you are shedding one of those telomere ends. And for a child, it looks like a closed rose, and for an adult it looks like an exploded turkey. That's your telomere. Every time you break off from something that you considered from heart to be your thing, and that other thing is in essence left floating, you break off one of those. You have about 50, then you die. Once your cells, because they don't do it in unison, reach a point of being at roughly that 50, those cells can't divide anymore. thus when they get cancer, they can't self-eliminate. Because to do so would create an open scar in your tissue because the neighboring cells wouldn't be able to replicate themselves to fix that tissue. That's what happens. According to current research, if you use all the methods available that are currently completely theoretical and based on a single case, but let's assume that it works for you, you at the same time get the world's best cancer treatment, because many of these treatments will give you cancer. So you will have to preemptively be on cancer check, and in some cases, perhaps even cancer preemption. There will be steps taken. But assuming you don't die of any complications, with current technology, you're looking at about 120 years. That's what you're looking at. But in 120 years, if you're 40, in 80 years, the technology to extend your life has once again advanced. And you may get more, but those are theoreticals. I don't believe anyone being born in the Victorian era, the era up to World War I, believed that they would be around to see the year 2000 when you're born in 1890. But some of those people did. And it was absolutely inconceivable in an era where the average life expectancy at the time of their birth was 35 to 45, that commoners somewhere lived to be 120. So if you do everything that you can to extend your life, you may be able to hit the hundreds without too much effort. But it does require effort. If you let your body be and you just float through life, you're gonna die at some point. Most likely when you hit your first snag, because your body is like, fuck this, I'll go to another life. But if you slowly groom your psyche to enjoy your life, in that you take a thing that you hate and perform it unto you in a positive light, and train your body and your mind to associate the fact that your body is alive rather than that you are in some body, that you have gone through a specific process by which your body is indispensable to the soul-mind connection, that it's not just some random guy floating around enjoying the mood of the thing, but rather a piece of the brain that actually works, then it is conceivable to talk of lifelines and efforts that are manageable but are in the unfathomable range. And I will leave it at that. I would like to focus on trying to find meters or indicators by looking at the data of what has most increased life expectancy, literacy, individual freedom, etc., and combining all those into a single criteria. And I believe currently that's the Human Development Index, but I don't like using indexes that I don't completely understand. That's why I'm more in the favor of making my own index, but similar index, and carefully checking that data on what seems to increase and what seems to decrease the HDI. And then very slowly going towards the increase end, knowing that that might be this generation's optimum. It's not a religion, most likely, that will hold beyond generations, because I've seen, now that I'm old enough, what the next generation thinks of the universe and what needeth be changed and so on and so forth. And it is so dreamlike in their complaints. They are absolutely true, but presented in such a dreamlike manner, in the mood that needeth be the mood, that their connection with my generation's very, let's say political, where actions need to be with a community where things as a group need to change and so on and so forth is rather completely non-existent. It is weird. And it is difficult to adjust to. So I can't even imagine what 3 generations of adjusting might be like, because you have to remember consistently your own generation and its rules while you enjoy the other generations. Because if you forget the previous generation, you get born into the next generation instead of just living in it as an object of the other, which you can do, but it once again requires you to incarnate, meaning that you'll lose a part of your life that you consider to be the normal lifespan. You can do it in that you can literally take the time it would take you to process whatever it is that you do and what society deems to do in opposite to it into a hallucination that you live through. And that hallucination's most important crossover points with all individuals can be of you choosing in how illusionary it is. But if you, for example, face 10 years in prison for murder, you can hallucinate for 10 years and wake up 10 years older the next day and then realize why you hallucinated without memories of what you hallucinated. Your mind can do that. Just saying casual things here. You can literally program your mind like in the movie Click. You can write down instructions and click play and wake up later. However, it does always consume your actual life expectancy. My opinion is life expectancy and that Horde HDI improvement as a slow indicator of what's going on. Though, like I said, I would prefer my own indicator. The HDI seems to be so blatantly in the Western system's favor that it seems to be incorrect. If it works, there ought to be in all nation regions, at the least, definite blots of very good and very bad performance, if it works. I cannot believe the HDI of Midtown Chicago is better than Midtown Mogadishu. I cannot believe that. I mean, if you force me to live in either Chicago or Mogadishu as a Finn, I'd live in Mogadishu. I know it's in Somalia. I'd still live there as opposed to Chicago. Now, if you want to talk New Orleans,